An oscillator is a circuit that produces a periodic waveform on its output with only the DC supply voltage as an input. A repetitive input signal is not required except to synchronize oscillations in some applications. The output voltage can be either sinusoidal or non-sinusoidal, depending on the type of oscillator. Two major classifications of oscillators are feedback oscillators and relaxation oscillators.
One type of oscillator is the feedback oscillator, which returns a fraction of the output signal to the input with no net phase shift, resulting in a reinforcement of the output signal. After oscillations are started, the loop gain is maintained at 1 to maintain oscillations. A feedback oscillator consists of an amplifier for gain and a positive feedback circuit that produces phase shift and provides attenuation. A second type of oscillator is the relaxation oscillator. Instead of feedback, a relaxation oscillator uses an RC timing circuit to generate a waveform that is generally a square wave or other non-sinusoidal waveform. Typically, a relaxation oscillator uses a Schmitt trigger or other devices that changes states to alternately change and discharge a capacitor through a resistor.
For oscillation to occur, the phase shift around the feedback loop must be effectively 0 degrees, and the voltage gain ACL around the closed feedback loop must be equal to 1 or unity.
R1 and C1 together form the lag portion of the circuit. R2 and C2 form the lead portion. The operation of this lead lag circuit is as follows. At lower frequency, the lead lag circuit dominates due to the high reactance of C2. As the frequency increases, XC2 decreases, thus allowing the output voltage to increase. At some point specified frequency, the response of the lag circuit takes over, and the decreasing value of XC1 causes the output voltage to decrease. R1 and C1 together form the lag portion of the circuit. R2 and C2 form the lead portion. The operation of this lead lag circuit is as follows. At lower frequency, the lead circuit dominates due to the high reactance of C2. As the frequency increases, XC2 decreases, thus allowing the output voltage to increase. At some specified frequency, the response of the lag circuit takes over, and the decreasing of XC1 causes the output voltage to decrease. To summarize, the lead lag circuit in the Wien-bridge oscillator has a resonant frequency at which the phase shift through the circuit is 0 degree, and the attenuation is 1/3 below resonant frequency. The lead circuit dominates and the output lead the input above resonant frequency. The lag circuit dominates and the output lags the input.
The Wien-bridge oscillator circuit can be viewed as a non-inverting amplifier configuration with the input signal fed back from the output through the lead lag circuit. Recall that the voltage divider determines the closed loop gain of the amplifier.
As you know, for the circuit to produce a sustained sinusoidal output or to oscillate, the phase shift around the positive feedback loop must be 0 degrees and the gain around the loop must be equal unity or 1. The 0 degrees phase shift condition is met when the frequency is Fr because the phase shift through the lead lag circuit is 0 degrees and there is no inversion from the non-inverting positive input of the op-amp to the output. Initially, the closed-loop gain of the amplifier itself must be more than 3 until the output signal builds up to a desired level. Ideally, the gain of the amplifier must then decrease to 3 so that the total gain around the loop is 1 and the output signal stays at a desired level, thus sustaining oscillation. The circuit in the rightmost figure illustrates a method for achieving sustained oscillations. Notice that the voltage divider circuit has been modified to include an additional resistor R3 in parallel with the back-to-back Zener diode arrangement. Determine the resonant frequency for the Wien-bridge oscillator in the figure. Also, calculate the setting for the feedback resistor assuming the internal drain source resistance on the JFET is 500 ohms when oscillations are stable.
To find the resonant frequency, we use the formula 1 over 2 pi RC. For the lead lag circuit, R1 equals R2 equals R equals 10,000 ohms. C1, C2, and C3 are equal at 0.01 microfarad. Substituting the values to the formula, we get 1.59 kilohertz. The closed loop gain must be equal to 3 for oscillations to be sustained. For an inverting amplifier, the gain expression is the same as for a non-inverting amplifier. The formula to be used is Rf over Ri plus 1. Ri is composed of R3, which is the source resistor, and RDS. Substituting, we get AV equals Rf over R3 plus RDS plus 1. Then solve for Rf, we get 3000 ohms.